Okay, let's continue our discussion on power quality. The main thing, or the main power quality related event to power electronics is harmonics, right? So where do we find harmonics? Well, we talked about the definition of harmonics, right? Harmonics are integer multiples of frequency of the operating frequency of the system, right? So fundamental frequency could be the 60 hertz, 50 hertz, 400 hertz, whatever frequency that whatever the main frequency that the electrical system is using, right? That defines the fundamental frequency, right? So integer multiples of that would be the harmonics, right? So where do we find harmonics? First, related to this class is power electronic circuits. I mentioned last time that I think for you it's really important to know not just the good things about power electronics, but also the drawbacks, right? The disadvantages, the challenges, the technical problems that power electronics unfortunately give us, right? So the main thing that power electronics inherently has is, because it's switching right internally, is that it would produce waveforms, currents or voltage that contain harmonics, right? And so power electronic circuits will be one of the main or major source of harmonics, right? Such as the uninterruptible power supply systems, motor drives, rectifiers, filters, fluorescent ballast, power supply that's powering PCs, right? And the harmonic itself individually will vary in amplitude and phase angle depending on the harmonic source, right? Here's an example of a single phase rectifier that has a capacitive output, and it gives you that kind of input current, right? Pulsating input current, and it's not sine wave, right? So as soon as you see that the waveform is not a sine wave on the AC side, then you know that you'll be dealing with harmonics, right? Here on the second picture right here, we have a motor drive system where the input on the front end is a rectifier, three-phase rectifier, right? That's what you learn in EE411. And then on the other side, you have the three-phase inverter. That's the circuit that we learned in this class, right, last week. Right? And here we convert from AC 60 hertz to DC, and then from DC back to AC at different frequencies, right? And at the input, if you measure the current, it will look something like this. This is actually a cleaner version of the current. When you have big capacitors sitting on in the middle of the two stages, then the current will be even worse than that. It will look something like this, right? And that has to do with these diodes, right? Waiting for its cathode to be less than anode, right? As you are charging this cap, you have voltage at the anode of the diode. At the cathodes of the diodes. Right? So as soon as the sine wave at the input is larger than that voltage, then diode conducts, right? So it takes time for that. That's why you see this discontinuity in the current, okay? And then non-power electronic circuits, these are the different equipment that could produce harmonics, arc furnaces, right? That's an equipment that can produce not just harmonics, but also interharmonics, right? What are interharmonics? Interharmonics are frequency components that are not integer multiples. So it could be, for example, 1.5, 3.3, right? So it's not an integer multiple of the fundamental frequency. And then we have transformers as well. So transformers, it's interesting to see that a transformer could also produce harmonics, but only if you operate the transformer on the non-linear region, right? So if you look at the saturation curve of the transformer right here, right? That's the BH curve, hysteresis curve that you learned from 295, I believe, right? You're supposed to operate the transformer along the linear region, which is right there, right? So if it's AC, then it's going to go, positive cycle, negative cycle, and so on and so forth, right? So as long as you operate the transformer in the linear region, then you're fine. No harmonics will be produced, right? You would apply sine wave voltage, and then the current that the transformer will draw will be sine wave as well. Oops, sine wave as well. Right. There you go. Right. Again, this happens as long as you are operating the transformer in the linear region. But then if you somehow, if the voltage that is exposed to this transformer somehow goes into the non-linear portion of the BH curve, then you're going to have a problem, right? Such as this picture right here, right? So if you look at this picture, you see that the voltage that is being applied to this transformer or imposed to this transformer, right here, that's the voltage. So imagine this voltage appears across the primary side of the transformer, and that voltage, as you can see, that is the voltage that would be in the nonlinear region of the BH curve. See that? So because of that, the current that will be produced by this, that will be drawn by this transformer, right? If you impose a voltage that force the transformer to operate in the nonlinear region, then the current will be non-sinusoidal, will be something like this, rich in harmonics, especially triplet harmonics. Right. So, so then the next question is, how is it possible for voltage to be, imposed to this transformer that would be operating the transformer in the nonlinear region? How would it be possible for this voltage to be this big? Because obviously you need to have a big voltage, right? See that? You need to have a big voltage. So rather than the normal operating condition, normally when you operate the transformer, the voltage would be maybe about this low, maybe, right? Like that, right? So if the voltage, the system voltage is maintained to be within this range, then you can see that that's within the linear region of the transformer, right? So how could it be? How would it be possible for voltage to go above the nominal value? Well, this is possible when the system is lightly loaded, right? When the system is lightly loaded, then voltage will be higher than the nominal value, right? Just like a regular, AC voltage, if you by Ohm's law, that's what's going to happen, right? I mean, if I simplify the equation, this is the load right here, right? Let's say this is 120, right? 120 volts. So during, if we, this is not 120, this is larger than 120, right? That's the source. So the way we design the system is that at full load, this voltage right here should be 120 RMS, right? Right. So that would be how we design it. But then what happens when the load is not full? What happens is if the load is not 100%, right? That would happen, right? Every day that would happen, right? So then this voltage is going to go up, right? Higher than 120. It's going to go up, right? Because you have less current, right? Less load means lower load means less current. Less current means less drop across this impedance. Less drop means higher voltage by KVL, right? If this is fixed voltage at the source, right? And you can see that V load, if I call this V load, is going to be equal to V source minus V drop across the line, if this is V drop, right? So at light load, this V drop is less or is smaller. That would make the load voltage bigger. And that's what is being seen by the transformer. At light load, it will be seeing larger voltage. If that happens, then transformer becomes, or a transformer would operate in the nonlinear region, and that would cause the transformer to draw nonlinear current. Does that make sense? Any question on that? Okay. Motors, the same way. Depending on how you design the windings in the motors, what do you call it? The winding slots, right? We are we're producing sine wave from the motor based on how many windings you put into the rotor and the stator of the motor, right? And the more winding slots you put, then the more sine wave the output would be, right? And so this is just an exaggeration, right? If you have a small number of winding slots on the stator, for example, then the sine wave is not going to be smooth, right? So that also creates harmonics. Okay. Any questions so far? So I think I mentioned three different sources, right? Power electronic sources, power electronic circuits, transformers, and motors. Those are the three different component equipment that could put out harmonics. Where do harmonics come from? In general, any electrical load that does not have a linear relationship between voltage applied to it and the current through it, then is called nonlinear load, right? So any nonlinear load would draw harmonic current. Right? So any loads, there's another definition of nonlinear load. A nonlinear load is any load that whose Lissajous figure is not an ellipse, nor a circle, nor a straight line, right? So let's say that I have this voltage and current of the load. Let's say this is a voltage across the load, and here's the current through the load, right? And you can see both are sine waves, right? So we don't expect to see harmonics, meaning this is a linear load, right? If you take XY plot, right? Everybody in this class should know how to get XY plot on the scope, right? Instead of a time domain waveforms, you can change the mode on the scope to XY plot, right? Where X could be the current, Y could be the voltage. So if you plot voltage against current for this, for this set, voltage and current, you get a linear plot like that. And this is called Lissajous. I don't know if I pronounce it correctly. Lissajous figure, right? VI plot basically. So if it's a linear circle or an ellipse, then that would indicate that the load is linear load. Anything else, that's going to be nonlinear. Same thing here on the second example, I have a current that is lagging the voltage, right? But if I change the plot to XY plot instead of time domain plot, then I ended up with, excuse me, let me drink first. I would end up with an ellipse, right? Right there. That's the Lissajous figure for this example, where you have a lagging current. If the amount of lagging phase angle of the current is exactly 90 degrees, then you're going to end up with a circle, right? So that's an indication that that the load is linear. But what happens if I have this kind of a setup, right? Where I have voltage, a sine wave, and then current that is pulsating. Again, this is coming from a single phase rectifier with a capacitive load. Then if you do XY plot of these waveforms, then you get Lissajous figure that is neither linear line, straight line, nor it is a ellipse, nor it is a circle, right? So then we know by looking at the shape of the Lissajous figure whether or not a load is linear or non-linear. Okay, so this is an example where we have a non-linear load. Any questions so far? No? And this is a table that shows common nonlinear current waveforms and their distortion level for your reference. A type of load, single phase power supply, you already seen it twice already. Semi-converter, 6-pulse converter, see that right there? The one that I drew earlier. That's a big capacitive load right there. 6-pulse converter, capacitive smoothing, right? That's with inductor filter, and 6-pulse converter with large inductor as well, or that's on the output. That's sorry, this is at the input, that's at the output. 12-pulse converter, AC voltage regulator, you've seen it in EE411, right, with fighting angle, and then fluorescent lighting. So just different type of nonlinear loads, right? And here's the source of this table in case you're interested in looking at more on this topic, right? Why worry about harmonics? Well, this is an example that hopefully shows you that you should be worried about. You should be, you should worry about harmonics. You should be concerned about harmonics. Here's an example where I simplify the system, of course, right? I have the source side right there, right? Let's say from the utility side, the secondary side of the transformer, right? Represented as a voltage source. And then from the secondary side of the transformer, it goes into the distribution line, goes into a house, into your house, into other houses, right, in the neighborhood, right? So all of these houses are connected to the same secondary winding of the transformer. But in between secondary side of the transformer to these houses, there's some impedance, right? So that's line impedance, okay? So then, okay, let's say that all of these houses, including your house, right, are drawing linear loads, right? So no harmonics, clean sine wave, right? Current-wise. However, there's one neighbor, let's say, that's running a business, maybe some kind of a, I don't know, manufacturing, small manufacturing, I don't know, some small factory that is running, machine with adjustable speed drives, let's say, right? That would draw harmonics. Let's say that harmonics goes into this load, okay? So now you have clean current going into these houses, but then bad current with harmonics goes into this one house because they're running big adjustable speed drives, for example. Right? So then what's going to happen? Okay, the voltage here is clean, right? That's a source side. So the voltage there is a sine wave, pure sine wave. Okay. Now, if you do KCL, well, before I do that, current will be going through this distribution line, right? Going through this impedance, and we're going to have voltage drop across this impedance, right? By Ohm's law, you're going to have voltage drop there, and then that voltage drop is equal to Z of S times current through it, right? And how much is the current through this impedance? That's got to be by KCL, summation of all these current, right, through these different houses, right? Now hopefully you see the problem now, right? Because if you go ahead and do a summation of all the currents, right, even if there's only one house that's creating harmonics, right, other houses are drawing sine waves. Go ahead and add, sine waves to this, corrupted current. How are you gonna end up with in terms of the shape of the current here, right? Is that current gonna be a sine wave? Most likely not, right? It will not be, right? So if you do KCL at this node, right, corrupted current from here plus sine wave currents from the other houses, that's gonna produce a total current that is not going to be purely sine wave. It's going to be distorted, right? So distorted current. meaning there's some harmonics, right? You agree? Okay, if you agree with that, then the problem is that same current, the distorted current, the distorted total current, will have to flow through this impedance. And by Ohm's law, because of that impedance, we have voltage drop across this impedance, right? Let's call it the V line, right? Now, if you draw the shape of this voltage drop across the impedance, is that going to be sine wave? Of course not, right? By Ohm's law, V line is equal to I line times Z, ZS, and I line is distorted. Oops, distorted, I misspelled. So if I line is distorted times, some impedance, constant value, right? Constant constant amplitude and constant phase angle, then of course voltage, the shape of the voltage will also be distorted. You agree so far? Okay. So now this is pure sine wave, let's just say. Right? Now I have voltage drop that is distorted here. Distorted voltage. And go ahead and do KVL around this loop, right? And you can hopefully clearly see why you need to be concerned about harmonics, right? Because if you do KVL around this loop, then you know that voltage across this house is going to be distorted as well, right? So this voltage is going to be something like this. Going to be distorted, right? Now, unfortunately, right, other houses are in parallel with that one house. So therefore, even though your house does not have any harmonic load or nonlinear load, voltage appearing across your house will also be distorted because of this neighbor. Okay, and you pay the price of having this, a non-sinusoidal voltage, because then that voltage divided by the impedance of your house, that would give you nonlinear current as well, with all the problems that we're gonna talk about next. Okay, so you should be worried about it. You should be concerned about this, right? Because of the fact that voltage is being shared, right, with the neighbor that causes this problem. Any question on that? Hopefully that's clear, right? Okay. So why should we be concerned about harmonics from engineering perspective? Can cause many problems. Nuisance tripping of circuit breaker. The circuit breaker is being controlled based on zero crossing. Supposed to see two zero crossings per one cycle, but because of harmonics, you could apply notching, for example, you could see more than 2 zero crossings. So you can have, you could run into nuisance tripping of circuit breakers. Then harmonic resonance, we'll talk about it later. Capacitor bank failure, excessive heatings, transformer overheating, skin effects, all of these, right, problems are created by harmonics, right? I'll go back to this capacitor bank failure next when we get to the capacitor resonance. And then from business perspective, harmonics are also a problem because it could increase maintenance and replacement costs, interruption and downtime cost, reduce system capacity, thus increase capital expenditures. Yeah, and those are the reason why we need to be concerned with harmonics. Okay. Any questions so far? All right, let's talk about the bad impact that harmonics have on our electrical systems in more details. First one, effect on conductors, right? All right, so remember the harmonics are high frequency components, right? Higher than the fundamental component. Harmonic current cause additional I square R heating in every conductor through which they flow. This is due to the increase in skin effect, right? As well as proximity effect, which I don't think I listed here. Yeah, a conductor can be carrying rated RMS and current and still overheat. Increased losses means a less efficient power systems and higher electric bill. You remember skin effect, right? If I draw, for example, a cable or a wire, cross-sectional area of a wire, and if we inject DC current, then the electrons would populate the entire cross-sectional area, right, of the wire. If it's DC, right? If it's AC, then we have the skin effect, right, where electrons being pushed away from the center of the wire, so creating a halo effect. So electrons will populate everything else but the center of, so the center is basically empty. No current flows into the center of the wire. Right? That's the skin depth right there, right? You learned from, I don't remember which class, 335 maybe, right? So the higher the frequency, the smaller the skin depth, right? The higher the frequency, the smaller the skin depth. So basically electrons are being pushed out more to the surface, the higher the frequency, creating even bigger halo effect, right? Okay, so that's skin effect. And why is this bad? Well, by not utilizing the entire cross-sectional area, that would mean physically, that would mean that we increase resistance of this wire, right? So resistance of the wire now has been increased due to the skin effect. So imagine if this current, right, the AC current, 60 hertz, already is giving us this problem. Now within that 60 hertz current, we have harmonics, higher frequencies. Now we're creating, more electrons that are being pushed out to the surface, right? Basically more resistance, right? Increased resistance due to harmonics, right? Okay, so that is the first problem that we learned from harmonics, how it's affecting conductors. Skin effect, right? Proximity effect happens if you have two wires nearby, right? Skin effect is the effect of frequency to itself, right? So just a single wire, individual wire to itself, that's skin effect. Proximity effect if we have two wires, right? Close to each other, right? And depending on where current flows, this is the one that I keep mixing up. Let's see, one is this way, and this way. If one is going into, and the other one is going, if both of them are going into, maybe we can see the flux by right-hand rule. That one's canceling, so that one's okay. If the other one is leaving, right, instead of entering, so then you can see by right-hand rule, the flux around that left wire is going to be going up in between the wires. So if you look at the area between the wires right there, from the right cable, if we go ahead and do the right-hand rule, right? The magnetic flux produced by the right cable when the current enters is going to be clockwise, right? In between the wires, it's going to point up, right? Okay, and then on the left wire, if the current is leaving, and go ahead and do the right-hand rule, that's going to be counterclockwise. So right in between those two wires, the magnetic field is also stronger, right, going up in the same direction. So you can see that the two magnetic field adds up really strong in between the two wires. So what's going to happen in that, in this case, is that you have proximity effect, right? If I redraw the two wires again, right, because magnetic field is so strong in the middle, electrons going to be drawn to that side, right? So creating proximity effect, something like that. So the way the current is populating the cross-sectional area is going to be pull toward the center, pull toward the, not the center, toward the area between the two, toward the point between the two wires. Okay, so that's proximity effect. Again, the impact will be the same, increased resistance. Any question on this? All right. So imagine if you have higher frequencies, then you have even bigger magnetic flux or magnetic field, I should say, in between those two wires. All right. So that's the first bad impact of having harmonics. Right? Effect on conductors in terms of skin effect and proximity effect. Increased resistance, basically. The second one right here, effect on the phase sequence. Right? For those of you who took EE411, you know what the sequence is. Oh, actually, everybody should already learn this in 212. Right? If you have a three-phase system, right, ABC, right, the three-phase system or voltage, for example, three-phase voltages will spin, right, in either clockwise or counterclockwise, right, basically. If it's clockwise, sorry, if it's counterclockwise, that's positive sequence. If it's counterclockwise, if it's counterclockwise, it's positive sequence. If it's clockwise, is negative sequence, right? Or the way we explain this is really not based on the direction of the rotation, but rather by using reference point, reference line in this case. So let's say I have VA right there, VB right here, VC right there. So VA, VB, VC, right? This frame rotates at the same time, right? This frame ABC, they rotate at the same time. And depending on the frequency, if it's 60 Hertz, then this frame, right, all three voltages, like this frame right here, will spin, rotate 60 times per second, like 60 cycles per second, right? Okay, if it's 50 Hertz, then 50 cycles per second. Now, typically the reference rotation is counterclockwise, right? So counterclockwise, this way. Now, if I place a reference line, let's say over here, reference line, right? As this frame is rotating, which one is going to pass by this line first? VA, right? VA is going to pass by first. Who's going to pass by next? VB. Who's the last? VC, right? So imagine this frame rotates counterclockwise. A is going to come by first, B is going to come by next, and C will be the last, right? That's called positive sequence. A negative sequence, if I have the order swap like this. So this one is VC and this one is VB. And go ahead and do the same thing. As this frame rotates counterclockwise, which one's gonna come by first through this reference line? Still A. Who's next? That's gonna be C. Who's gonna be last? That's gonna be B. So if that's the case, that's gonna be negative sequence. So positive sequence is when the order is at which the voltages are passing by this line is ABC. That's called positive sequence. If the order is ACB, that's negative sequence. Okay. All right. We're going to assume that this is all balanced three-phase voltages. Okay, 120-degree angle between the three-phase voltages. All right. So that's sequence. There's also zero sequence. Right. So that's positive sequence, negative sequence. Zero sequence is when A and B and C are all at the same angle. A, B, C are all at the same angle. That's called zero sequence. Okay, so there are three different sequences: ABC, ACB, and then zero sequence. Positive, negative, and zero sequence. Okay. All right. I'm not going to discuss more details beyond that. 406, people who took 406, they learned this, and also 407. So in three-phase power system, we normally assume an ABC sequence or positive sequence. If we watch the rotation of the phasors, phase A would come by first, as I explained earlier, then you get ABC. If you have the other order, then you have ACB. and then if they all rotate at the same time at the same angle, that's zero sequence. Okay, so positive, negative, and zero sequence. If harmonics exist in the balanced power systems, then the three voltages can be expressed by this equation right here. Notice that the three voltage equations, the three-phase voltages, has H. They have H in their equation. H is the harmonic number, right? So if the three-phase voltages have harmonics, then they follow these equations, right? Okay. The first one, as you can see, this is assuming ABC sequence. How do I know that? These three-phase voltages follow ABC or positive sequence. How do I know that? From the angle. Right, the first one, you can see the reference is theta H. The second one is theta H minus 2 pi H pi 3. See that? So that's minus, and go ahead and put H equal to 1 for now. So you can see that's minus 120, right? So the first one, VA, is at 0 degrees. And then the second one is at minus 120 degrees, right? Minus 2 pi over 3, that's VB. And then the last one is plus 2 pi over 3, that's plus 120 from A, okay? So that's your VC, that's plus 120. So that's how I know that we are assuming that we're gonna start with positive sequence. Okay. If that is the case, then let's take a look at what happens with those three equations when H is equal to 1. So that's fundamental component, right? H equal to 1. So those three equations becomes or simplify to these three equations: VA1, VB1, VC1. Fundamental component of A, fundamental component of B, and fundamental component of C. Right? Go ahead and plug in H equals to 1 on the previous three equation, and you get this equation for A, for B, for C. Right? And what do you learn from this equation? Turns out to be that it is a positive sequence again. Right? See that? Minus first and then plus. So B is minus 120 degrees away from A. C is plus 120 degrees away from A. Right? So just like this picture right here. Right? That's positive sequence, isn't it? A first, B next, and C last, right? Okay, any question on that one? What happened if I plug in H equals to 2, right there? If H is equal to 2, then of course the equation changed now to these three equations, right? So the second harmonics for A, second harmonics for B, second harmonics for C. Look at what happens at the look at what happens to the three equations well, after you plug in H equals to 2. Look at the angle. VA is still at 0, right? But look at B. Look at B. It's plus 2 pi over 3. Look at C. It's minus. So now I know that when you plug in H equal to 2, VB is going to be plus 120 with respect to A. So that's this right here. Right? Plus 120 is that way. And C is minus 120 with respect to A. So that's this way. Right? So now I know that the sequence will be A, C, B. Right? So that's negative sequence. Interesting, huh? So that when you plug in H equals to 2, the sequence changes from positive sequence, right, for H equal to 1, to negative sequence when H is equal to 2. All right. Now, what's more interesting is when you plug in H equals to 3. Go ahead and plug in H equal to 3 to the original three equations. Look at what you end up with. VA, VB, VC. You know, third harmonics for A, third harmonics for B, third harmonics with C. Look at what happens to the three equations. They all have the same angles, right? No 2 pi over 3 anymore. See that? That means when H is equal to 3, A and B and C are all having the same angle, right? That means that H equals to 3 follows zero sequence, right? Now, graphically, right, you can simulate this, which I did with OrCAD. you can see that when H is equal to 1, right, you can see, look at the peaks, right? A first, B next, and C last for first harmonic. Second harmonics, you can see that A first, C is next, and then B is last. And then for third harmonics, you can see that all three lined up, right? Same time. All three are happening at the same time, same angle. See that? Now, what is so dangerous? What is the big deal about this zero sequence? Yeah, you have to be concerned about this as well. Now, if you look at positive sequence, imagine if these are currents, not voltage, right? Imagine you have a 4-wire system, such as this. I'm gonna draw this. This is dangerous, okay? The third harmonics, we call it triplet harmonics, are dangerous. Here's IA, here's IB, here's IC, okay? This is supposed to be neutral, right? IN, okay? Now, if IA, IB, IC, they're balanced, right? And they follow positive sequence. If they follow positive sequence, go ahead and add. Oh, what is that? Right here. Let me use my mouse. Right there. Right, so let me erase this. Right here, go ahead and change those two currents, IA1, IB1, IC1. Right? What happens if you add those three currents? You're going to end up with how much?
0.
0, because they're balanced, right? If you add them up, it's going to be 0. So IN1 is going to be 0. What about second harmonics? It follows negative sequence. Go ahead and change those V's to I. So IA, IA2, IB2, IC2. What happens if you add the 3? Is equal to 0 again,
0.
right? So at this node is when you add all three. By KCL, all three currents add to this node, right? Giving you IN. So since harmonic 1 follows positive, therefore IN, IN1 is equal to 0. Same thing with H equal to 2. You have negative sequence. Since they're balanced, again, there you go. IN2 is also 0 amps when you add them, right? So IN2 is also 0 here. But what happens with H equal to 3? Right there. Go ahead and add them. Add all three currents. Is that going to be 0? Of course not, right? Because they all have the same angles. That's what's dangerous about these harmonics, right? Harmonic number 3 and multiples of it. When H is equal to 3, it follows 0 sequence. That is dangerous because now IN3 is not equal to 0 anymore, right? To the point that it can be larger than the line current itself, right? Normally, if they are balanced, no harmonics, typically we size this neutral conductor to be less than 1/3 of the line current. So we typically size the conductor, IN, the neutral conductor, to be less than 1/3 of IA or IB or IC. But if the currents, line currents have harmonics, then this is no longer true, right? Because the neutral conductor could actually carry more current than the line conductor, which is dangerous, right? So now you know that triplet harmonics, not just number 3, but also multiple of 3 is dangerous. Yeah, right there. So if I continue calculating the sequence, right? So I did the first 3, right? Harmonic number 1, number 2, number 3. Number 1 is positive, number 3 is negative, number 3 is 0. And if I do H equal to 4, it goes back to plus again, positive again. Number 5, negative again. Number 6, 0 again. So you can see that multiples of 3, right? Those are what we call triplet harmonics, right? So now you know, if somebody said, yeah, triplet harmonics are dangerous, now you know why, because they add up, right? They follow 0 sequence. even under balance condition, they add up. Okay, I just explained this earlier, that the effect of harmonics, right, could be dangerous to three-phase with neutral conductors, right? Yeah, with nonlinear loads, there will be harmonic currents, and the neutral conductor may carry more current than the phase conductors. That could cause overheating, and typically neutral conductors are not protected by circuit breakers, right? So even if the current is high, circuit breakers, since it is not protected, then the current will just flow through these neutral conductors until this neutral conductor got so hot and could catch, you know, fire. Okay, so the way to overcome the problem is by having a bigger neutral conductor or separate neutral conductor for each phase. Okay, any question on that one? Okay, next, effect on power factor correction capacitors. Capacitors don't create harmonics. What they create is resonance, right? So power lines is mostly inductive, right? So if you are connecting a capacitor, right, to correct power factor, for example, right, you connect it, then you create resonance, okay? So this resonance could be dangerous because if let's say that this current flowing through the line has harmonics, right? And I'll show you a picture right here, right? So if you draw the body plots of a second order system, right, L and C, that's a second order system, right? Then the body plots of that would be something like this, right? Gain plot. This is 0 dB, right? And when the load is heavy, so fully loaded, close to fully loaded, the damping ratio is very small. So then this will have a peaking effect, as you learned from 302, right? Very low damping ratio means you're gonna have peaking effect, percent overshoot. That's a gain, right? That's basically a gain. Actually, this is not 0 dB. 0 dB is right here for that. So gain of 1, and then you are introducing a gain if you have a peaking effect, right? Okay, so now that's what I have right here. Okay? That's the drawing for the second order system with peaking effect, right? Now, here's the 60 hertz component, right? Resonance typically very high, right, compared to 60 hertz, right? Resonant frequency is equal to 1/2 pi LC, right? So that's higher than 60 hertz. So let's say that's the 60 hertz right there, right? And here's the resonant frequency. That gives you the cutoff frequency, basically, right? So that's the resonant frequency. And let's say you have a peaking effect because of a heavy load in the system. Now, if the current right here, the system current has harmonics, and let's say that harmonics happens to be harmonics higher frequency, right? Higher than 60 hertz. Let's say that harmonic has a frequency right here. Would that be okay? I think so, because that's when you attenuate the harmonics. You're suppressing the harmonics, right? Because, you know, below 0 dB, that's a negative dB gain, right? Basically, you are suppressing the harmonic effect, right? But so this is fine if harmonic happens to be right here. But what if harmonic happens to be coinciding with resonant frequency? What if harmonic is right there? What do you think is going to happen? Well, that's a peaking effect right there, right? So then harmonics, if it happens to be right here, that's not good. Why not? Because the noise from the harmonic gets amplified by that gain right there. See that? So now you're going to get higher voltage than what you're supposed to on the system voltage, right? So when you turn on the capacitor will have huge spike because of the harmonic coinciding with resonant frequency, and that could damaging to other equipment. Does that make sense? So make sure that if you are in the future working for utilities and you know that there's a system that contains harmonics, you know, harmonic rich electrical systems, make sure that the resonant frequency of the system does not coincide with harmonics. If they are coinciding with each other, then you got to do something about it, right? You got to filter that harmonics. Any questions? Another thing about capacitor is this, right? That's one side of, that's one bad impact of harmonics to capacitor. Let's say that I have a power system and I have a capacitor, right, connected to the power system. And let's say that this current has harmonics, right? The problem with this, right, besides the resonant problem, right, besides this problem, the one that I just described earlier, another problem, which is a steady state problem, is this. The reactance of capacitance is equal to 1 over omega c, right? You can see that the reactance of capacitance is inversely proportional to omega, to frequency. That's not good for harmonics, right? Because harmonics are high frequencies, meaning capacitor presents a low impedance path for harmonics. So rather than going back to the source, right, harmonics will flow through this cap. Harmonic currents, not the 60 hertz, but a higher frequency currents, higher frequency harmonic current will flow through the caps and thereby overloading the cap, right? Overloading it, and you can damage the caps if it's too much harmonics flowing through these capacitors. Okay, so those are the two problems related to harmonics on capacitor. Number one, resonance coinciding with harmonics, peaking effect, right, over voltage basically. And secondly, is that capacitor presents a low impedance path for harmonics. The effect on transformers. Transformers are designed for 60 hertz. So when it sees higher frequencies, then it will heat up, right? The reason being hysteresis loss and eddy current loss, right? Hysteresis loss is proportional to frequency, and eddy current loss is proportional to frequency squared. So that's more dangerous than hysteresis, right? So if you have current flowing through this transformer that has higher than 60 hertz, then of course the transformer is going to get it's going to be heating up due to the higher frequency content of the current. That gives extra additional losses for hysteresis as well as eddy current loss. Okay, so that would overheat the transformer. Power factor now becomes more complicated to calculate, right? If you have simple, linear load, that's easy, right, to calculate power factor. That's just the difference between the angle. But what if you have current that looks like this? How do you calculate power factor? How do you calculate the difference between the voltage, phase angle difference between the voltage and the current? Now it's not so clear anymore, right? So that's why we need to have a new way of calculating power factor if harmonics exist in power system, in the electrical system. And here's the equation for calculating power factor if there's harmonics. You can see this is the first term multiplied by the second term right here, which is a big term, right? And the first term that relates to the original power factor, P over S, right? That's just fundamental component, V1 times I1, right? That's just the phase angle between the fundamental component of the voltage and the fundamental component of the current. The second term has to do what we call distortion power factor, right? That would include or take into account harmonics, right? So the first part of the equation is called displacement power factor. This is called displacement power factor. Whereas the second part, displacement power factor. Whereas the second part of the equation is distortion power factor. Okay. So without harmonics, you just need to calculate displacement power factor. With harmonics, you have to multiply displacement power factor with distortion power factor to take into account harmonics. right? So it becomes more complicated to calculate harmonics. Basically, that's what it is. What happened here? Okay. Any questions so far? So those are some negative impacts of harmonics existing in electrical systems. Okay, harmonic standards. There are some limits or some guidance, I should say, guidance for us to follow, recommendation to follow in terms of how much harmonic level should exist in an electrical system. When you're designing electrical system, you want to make sure that the harmonic limit, the harmonic level, does not exceed these recommended limits, right? And we have, I'm listing two different limits. The first one is from IEEE standard 519, and then the second one is IEC 1003-2, right? Bottom line is harmonic level is the responsibility of both the utility line and the utility side and the customer side. The utility side is mainly responsible for the voltage, because they're the one who's providing the voltage, right? Customers, we're the one who's drawing the currents. So therefore, customer side is responsible for maintaining current harmonics, right? So electric utility or utility companies are responsible for maintaining voltage harmonics in terms of THD. We'll talk more about THD, whereas customers are responsible in maintaining current harmonics. That's actually not THD, it's actually TDD right there, total demand distortion. So please change that to TDD. Sorry about that, that's TDD. Okay, then we'll talk about the difference between THD and TDD. These are just to give you some examples of the different harmonic, permissible harmonic levels for different level of voltages. For example, if the voltage level, system voltage, is less than 1 kilovolt, then the total harmonic distortion has to be less than 8%, whereas individual harmonics should be less than 5%, right? And then if it's higher voltage, as you can see here from the table, the higher voltage, the lower harmonic level is allowed in the system, which makes sense, right? Because the higher the voltage, the more power it carries, right? Same thing with the customer limits in terms of current, right? That's more to calculate actually. Now you have to calculate the ratio of short circuit current to the full load current of the load, right? And if the ratio is less than 20, then you can see the different levels for different harmonic numbers, right? Between 3 and 11, the levels will be at the most 4%, right? And these are all TDD, okay? Total distortion, total demand distortion. And if you sum them up or not sum up, the overall effect should be less than 5%. If it's between 20 to 50, then the overall effect should be less than 8% TDD, and so on and so forth, right? So this is this is an example of harmonic limits that we need to follow, or a lot of companies follow when they design their electrical systems. And there's another table for line notching, the depth of line notching, 10% for special apps, general systems 20%, dedicated system 20%. That's the amount of dip with respect to the peak value. And all of these harmonics are being measured at what they call point of common coupling, right? Yeah, because you have to measure these harmonics, right, at a certain point. And depending on the type of electrical load, that would determine where the point of common coupling should be, right? So PCC, I'm just going to call it PCC, right, which stands for point of common coupling. If it's industrial customers, big customers, then the PCC would be on the high voltage side of the transformer. If it's for commercial users as well as residential, then it's going to be on the low voltage side, right? So if that's the transformer right here, right, and that's the big factories, right, manufacturing lines, then point of common coupling, meaning the point where you measure harmonics will be on the high voltage side of the transformer. Whereas if it's commercial users, residentials, then it's going to be on the low voltage side of the harmonics, of the transformer. That's where you're going to measure harmonics right there. Any question on this? Okay, just more examples for point of common coupling, right? This is high side, high voltage side, so this must be industrial user, and on the low voltage side, that must be you know, residential as well as commercial loads. Okay. Which row of IEEE 519 should apply for this example? Customer is primary metered at 12 kV, so that means on the high voltage side. The current demand is full load is 200 amps, and then from short circuit analysis, the short circuit current is 5,000 amps. So from there, you can get the ratio of the two currents, right? 5,000 divided by 200, that's equal to 25. So to find the limit on the total demand distortion, if you go to this table, that's equal to 50, right? So 50 would be, the ratio is going to be, excuse me, 50, that's going to be, is it 50? I don't remember now. Oh, 25, not 50. I don't know why I got 50. So the ratio is 25. So if we go to that table right there, the ratio 25, that belongs to this row right there, 20 to 50. So between 20 and 50, the ratio of the short circuit to the full load, in our example is 25, so that belongs to the second row. Then the total demand distortion should be less than 8%, right? Okay. All right, now we go into how we can calculate harmonics, right? Quantify harmonics. With the presence of harmonics, this is the Fourier series of voltage and current that has harmonics in it, right? You can see that it is a Fourier series, or they are Fourier series for voltage and current. And the RMS, you can calculate the RMS. If voltage and current have harmonics, then the equation to calculate RMS will be this equation right here, right? From h equals to 1 to infinity of VH squared, right? And if you are using THD, you can also use this equation right there, right? Same thing for the current, right? And then what is total harmonic distortion? Total harmonic distortion of THD is the ratio of the RMS value of all the non-fundamental frequency terms to the RMS of the fundamental frequency, right? So non-fundamental, you can total them, and then divide it by the fundamental component, that gives you THD, right? So the equation for that, if the DC term is equal to 0, so no offset, that's going to be the equation to calculate THD, right? If the DC term is not equal to 0, if there is a DC offset in the voltage or current, then you use the second equation right there. And so those are two different equations to calculate THD, total harmonic distortion, right? Non-zero and zero DC. And I have this equation right there that describes current, right there. That current consists of three frequencies: the fundamental, the what is that? Second harmonics, right? And then third harmonics, maybe. No, what is that? Fourth harmonics, maybe. Yeah, it looks like fourth harmonics, right? So you have more than one frequency. And how do you calculate THD? Just plug in the equation from the previous one, except this one does not have any DC term, right? There's no DC offset. So you need to use the first equation right there, right? And notice that within the summation, that should be RMS, right? That's why I divided by √2. So be careful, because the equation gives you in amplitude, right? That's an amplitude, 20 times cosine. That's the amplitude of the cosine. So make sure that you divide it by √2 when you plug it into that equation. Okay, so 20 becomes 20 over √2, because what you need is RMS and RMS. Okay, now this one has DC term, see that? So now you can do you can use the second equation on the previous page, again making sure that now for DC, right, DC and RMS is the same, so don't do not divide by square root of 2 for DC, because DC is just flat, right? So the effective value of DC is the same as the DC, right? But for the other ones, you divide by square root of 2, right? So then you get that RMS, total RMS, and then you can calculate THD from there. Okay, and this shows you the danger of harmonics, right? Because if you have two wires and you measure current, right, through each of the wires using the same instrument, both can give you 100 amps, but it could happen, it is possible that even if both are measuring 100 amps, one of them is hotter than the other, right? How is that possible? Well, now you know from this chapter, you know that that is possible because the second one might carry harmonics, whereas the first one is only carrying the fundamental component, right? That's why the first one is not hot, because it's only 60 hertz component, whereas the second one, it has 60 hertz plus harmonics, and if you sum the harmonics plus the fundamental component, calculate RMS, it gives you 100 amps as well, right? So here's the mathematical proof, right? If you take the FFT of the first one, only has one component at 60 hertz, that's why it's not heating up. But if you take this FFT of the second current or the second wire, you can see we have more frequencies. Now, if you calculate RMS of all of these, it's going to give you 100 amps as well, right? So here's the mathematical calculation. These are the calculation to get the RMS. You can see that for the top wire, I get 100 amps for the RMS, right, from that one single frequency. For the bottom wire, right, I calculated the THD, and then from there I get the RMS. Look, it's also 100 amps, the same value, but they come from different frequencies, right, different content of the current. So be careful. Just because it is, let's say, oh, that's still 100 amps, that's still below the rating, right? It doesn't mean that it's safe if it has harmonics, right? So even if it's under the rating of the cable, it could still be hot because of harmonics. Okay. All right. Power calculation also becomes more complex, right? Because that's the equation for calculating power. You basically take power calculation from the same frequency, right? If the voltage has common frequencies, if there are common frequencies between voltage and current, then that's going to contribute to power, right? If voltage has this frequency right there, but not in the current, then how could you get power, right? For that frequency, voltage times 0 is equal to 0, right? So only those that have common frequencies between voltage and current will give you power, right? Will produce power, okay? We talked about this already, the power factor, right? So here an example that shows voltage and current, right? Equation they both have multiple frequencies, and you want to make sure that you pay attention to the frequency content. It looks like all three has the same frequency content. See that? So when you calculate power, you need to include all three because they have common frequency. All three are common frequencies. And this is just going through the exercise of calculating average power, VRMS, IRMS, THD, THDV, THDI, distortion power factor, and total power factor, right? So I'll let you do this yourself. These are just plug-in chug exercise, as you can see. Okay. Again, make sure that you take care of the square root of 2, right? Don't forget the square root of 2. In this case, if you look at the equation, sorry. You can see that's given by the amplitude 100 times √2. So when you do the THD calculation, you just need to include the 100, right, without the square root of 2. All right. Same thing here. Oh, this is another example that shows that we have voltage and current that have different frequency contents, right? I mean, the first one is the same, that's fundamental component. The voltage has 180 hertz, current has 180 hertz, but look, voltage has 300 hertz, but no 300 hertz for the current. Same thing for 540. So when you calculate power, this would be 0. That would be 0 as well. So only 3 components. Okay, so that should be seen by these. You should be able to see it from this calculation right there. Okay. Okay. Even harmonics, theoretically impossible for symmetrical signals about time axis, because again, I think I mentioned this last time, that in electrical systems, the voltage and the current are being derived from sine waves, right, from the generators, and generators are producing sine waves. That's why it is not common to have even harmonics, except if you are using a half-wave rectifier, which I also mentioned last time. Indices, we have THD, right? We already know what THD is. And remember TDD, right? Total demand distortion. And total demand distortion is equal to THD times fundamental load current divided by circuit rating, right? So fundamental component divided by the rating of the load. Okay, so that's the difference between time demand distortion, total demand, sorry, not time demand, total demand distortion with THD, right? So that's the difference. You have to multiply THD by fundamental load current divided by circuit rating. Let's see. Then the next one is distortion index. Distortion index is another way to quantify harmonics, as given by this equation right there. Describes the ratio of harmonic components to total RMS. So rather than ratio of harmonics to fundamental components, such as in THD, in distortion index, you take the ratio of the harmonics beyond fundamental divided by the total RMS of everything, including harmonics and fundamental. That's the difference. Right? I mean, notice if you go back to THD, the one that goes on the denominator is I1, only fundamental component. Here, you take into account the entire components, not just fundamental component, right? That's the difference between DIN and THD. And there's an example for you to calculate DIN. I'll let you go through this. And just one more. In this index, harmonic index, the last one is K factor, and this is specifically used for transformers. Remember earlier that transformers are being designed for 60 hertz, but if the current in the system have harmonics as well as the voltage, then you could replace the transformer with what they call K factor weighted transformers. Right? Some people also oversize the transformers, which is not a good solution to do. Right? It violates under UL listing requirements and does not properly address the problem if you oversize the transformer. The better way is to replace the transformer with K factor transformer. Of course, this is going to be expensive because these K factor weighted transformer are specially made for or to handle harmonics. How so? All of these right there, right? Thinner steel laminations, lower loss steel, larger conductors, right? So thinner lamination means limiting eddy current loss more, right? Special materials for the core, right? They can handle higher harmonics. That's why they're expensive. Okay? But the K rating, right, is an indication of the transformer ability to deliver power to a nonlinear load without exceeding its specified operating temperature limits. And then typical ratings include K4, K9 until K50. K4 means the transformer can handle a load that produces harmonic current that costs 4 times the normal eddy current loss. Remember I said earlier that eddy current loss is the most dangerous one because it's proportional to F squared. So that's what K4 means. It can handle up to 4 times the normal eddy current loss. Right? So how do you calculate K? This is how you calculate K right there. Right? K is equal to the summation of H squared times IH over IRMS squared. Right? And I have this example right here that shows you a table that shows you the harmonic content and how you apply the K factor equation from this table. Right? So straightforward, as you can see, you find RMS first, and then you plug in the RMS into the K equation right there as a total RMS, right? And then H is just harmonic number, IH is the individual harmonic current from the table, right? So you just sum them up like this, and at the end you get a number, right? So then if let's say that the K factor is 5.72, then what K rated transformer you should purchase? Well, you should choose the one that's higher than this, right? The one that's higher than 5.7. So if you go back to the different K rating available, the next higher one would be 9, right? 5.7 is what we calculated. So the transformer that we need to purchase is K9, okay? Are there any questions on this? So those are the different ways to quantify harmonics. THD, TDD, and DIN, and K factor.